Assalamualaikum dan a very good morning to all to all of you. Yeah, we are today Monday. Okay, Monday on the 28th of March. Okay, 28th of March. We are continuing into our second week of the semester. Okay. I'm doing the class today from KL sebenarnya. From KL doing continuing our online classes from Kuala Lumpur. Okay, I have ada some business ataupun ada sedikit urusan in KL, so I have to conduct the class from KL. Okay. Anyway, we will be doing our normal lectures. Today, even though saya di KL, we'll be doing our online classes as usual, okay, from 11 to 1. Hopefully, inshallah, at the end of this session, I will upload all our discussions dan juga all the lectures dalam e-learning. I have done that earlier for the first week punya lecture. Hopefully, some of you have already accessed the e-learning in UTM to download all the important notes, references dan juga project work. Okay, maybe sometime this week on Thursday we'll have a discussion on the project work for you to start off your project work. Grouping for your project work is you form your own groups. Okay, form your own groups because RC2 project work and IDP2 RC component is very closely related. It's actually referring to the same project, if I'm not mistaken. So it would be good if you could form the same group in IDP with RC2. But in your IDP you have about maybe 9 or 10 group members. So you need to half that, reduce that to half. So that one group in IDP is equal to 2 groups in RC2. Okay, that is my suggestion because you can always refer to the same grouping in IDP because the group project in RC2 will be reflected dalam IDP2. Yeah, where IDP2 is using the software application, whereas in RC2 we are doing it in a manual calculation. Okay. For the same project in RC2 dan juga IDP2. That is why I'm suggesting that you could take the IDP group that you have in your IDP, about 9 to 10 students, cut that into 2 so that you have 2 groups in RC2. Okay. The same group in IDP is now divided into 2 groups in RC2. So if you have around 4 to 5 groups in IDP, which means that you will be around maybe 8 to 10 groups in RC2, right? So that is my suggestion because it is closely related. The same project will be reflected in both RC2 dan juga IDP2. Okay. Cumanya in IDP2 you will be doing the same project but using a software application. In RC2 we'll be referring to the same project but doing it in a manual calculation. Okay, so there is a link between the project work in RC2 dan juga the RC component in IDP2. Okay, so anyway, form your own groups in RC2 and inshallah we will be discussing a bit on the project work this coming Thursday, okay, where we have our lectures from 8 to 10. So we'll be making use of that as our discussion on project work week number 2. Okay, you need to start early. You need to start early on your project work so that at the end of the semester it doesn't clash with your IDP. It won't clash with your maybe your FYP2, because this is your crucial semester for your FYP number 2. You need to present your results dan sebagainya. There is a presentation for your FYP. So if possible, we will try to finish everything up before the end of the semester so that you'll have more time to concentrate on your FYP dan your IDP dan sebagainya. Alright. So anyway, continuing from where we left off last week, we were doing the example number 1. Okay, basically we were looking at a single staircase, a single flight of staircase, where from the observation that we have come across last week was that it was a relatively straightforward case where we identified 2 supports for the staircase, and we finished this example, if I'm not mistaken, sampai to the detailing part. Okay, and for today we will proceed to example number 2. Example number 1 and example number 2 is actually very similar. It is just that in example number 1 we have these 2 supports indicated at the start of the staircase and at the end of the staircase. In example number 2 is where the support at the lower end di sini is now shifted to the end of the landing. Okay, so that is example number 2. So we'll be looking at example number 2. Any question on example number 1? Anyone? We also had a look at the additional reinforcement that we need to put into the detailing for the example number 1. There are some missing detailings. If you have a look at the previous lecture, we added, I think, another reinforcement over here as the top reinforcement, and over at the bottom part of this to ensure that there is no opening between the reinforcement. Yeah, and I also mentioned that this particular reinforcement, okay, this particular reinforcement is actually the reinforcement coming from the adjacent slab. It is not something that we designed in this staircase punya problem, right? And similarly, this reinforcement, okay, the bottom reinforcement and then crank up kepada menjadi top reinforcement, this is also the reinforcement coming from the adjacent slab. So what we did was we designed the reinforcement yang ini, okay, and then we continue sampai di sini. And then this part is actually the reinforcement that has been is not the reinforcement that we designed, but it is the reinforcement from the adjacent slab, right? Anyway, we'll continue dengan example number 2. Before we continue, any questions from anyone? Ada? Okay, I'm sharing this. Okay, hopefully everybody, because sini kadang-kadang line dia on, kadang off. Right, so bear with me for the next 2 hours. Okay, right, as I was saying earlier, example number 2 is very similar with example number 1. Cuma if you remember, we had apa nama, this initially was where the location of our beam was in the first example. Okay, in the first example, this was somewhere here. Okay, and now this beam has been taken right to the end of the landing. It means, and from the observation we can see here, the landing is now connected directly to the beam that is supporting the staircase. So now we have a condition where there are 2 similar supports, I mean 2 beam supports. One is located at the upper end of the staircase, and the other one is located at the end of the landing. Okay, right at the end of the landing. So again, from once we have identified where the supports and the positions of the support and what are the supports, in this case it is a beam support, and the location of the beam support is clearly indicated, then this would mean that now our span is from one end, center of support on the left hand side, right till the center of support to the left hand side. So this will now represent our span for the design of this staircase. This will now represent our total L, total span between center support to center support. And within this total L, now we have a combination where we have an inclined section, Okay, we have an inclined section together dengan a horizontal section. Okay, this is our horizontal section. We have an inclined section and a horizontal section within within a single span. Dalam rentang yang sama, within the span, we now have two components. One is the inclined section and satu lagi is the horizontal section. So because both these elements, the inclined element and the horizontal element is within a single span, therefore we don't need to differentiate. We don't need to design the horizontal and the inclined section as a separate component, design the horizontal section as a separate component, tak perlu. Because both this component is in a single span. Dalam rentang yang sama, within the span, within the single span, okay, within this L, we have both components represented dalam a single span. So one is that we can conclude that there will be no distinct perbezaan, okay, different design to be applied pada the horizontal section landing dan juga the inclined section. We will design both the inclined and the horizontal section as a single component. Okay, that is number one. Number two, the schematic for this staircase, kalau kita tengok on the right hand side, there is no more continuity. Beyond this beam, there is no more continuity. But on the left hand side, beyond the beam support di sebelah atas ni, on the top end, there is still continuity. So we can represent this staircase to be something like a continuous staircase. Okay, a continuous staircase. This is our staircase. Okay, I'm trying to figure out dia punya schematic of this. Okay, so this will be our staircase, and the supports will definitely be pada beam location. We have one support di sini, okay, and another support over here. So it means that kita punya staircase is now can be clearly identified sebagai a continuous staircase, but continuous only at one end of the support, meaning that it is still a continuous punya staircase, cuma it is continuous on one end sahaja, on the left hand support. It is not continuous on the right hand support, which gives an indication that the bending moment diagram would somehow look like macam ni. This would be the shape of the bending moment diagram. It is still considered sebagai a continuous staircase. Cuma we can say that this staircase is a continuous staircase representing the end span of a continuous beam. Rentang hujung rasuk selanjar. It represents the end span, rentang hujung of a continuous beam. So we have one negative moment on one side, on the left hand side, we have a negative moment, which means that we will need to provide for top reinforcement on the left hand side. Okay, we need top reinforcement di sini, and we need bottom reinforcement. Okay, bottom reinforcement between the supports. Okay, we need a bottom reinforcement di sini. Okay, to resist the positive bending moment, we need bottom reinforcement, and to resist top negative moment, we need top reinforcement on the left hand support. So this will represent our main reinforcement, tulang utama. Okay, main reinforcement. Of course, if you recall balik what you have done earlier in your slab design, when we have cases berkaitan dengan a typical slab, okay, a typical slab connected kepada L beam at the end of the slab, okay, we have our reinforcement for the slab. Di sebelah connection di sini, we still provide some top reinforcement. The connection between the slab dengan beam at the end, meaning the connection of the slab dengan the L beam. Yeah? We still need to provide some top reinforcement. This is to prevent cracking. Okay? We have some negative moment, even though theoretically it is zero bending moment, zero negative moment, but we expect because of the in situ condition between the slab dengan beam, maka there will be some negative bending moments ini, walaupun theoretically it is 0. Therefore, we still need to provide some top reinforcement over at the right hand support. Okay. Tapi this top reinforcement is sebenarnya just to prevent anti-cracking. It is an anti-cracking top bar where the landing is connected kepada the L-beam at the end of the landing. Kalau recall balik what you have done earlier in your slab design, whenever there is a slab connected kepada L-beam, at the end of the slab, we still provide some top reinforcement to provide some top reinforcement against what is called as the anti-crack bar, to prevent cracking that might occur on the top surface of the slab. So similar consideration, we still need to provide some top reinforcement di sini. But remember, this top reinforcement is not due to this negative bending moment. It is more as a good practice untuk mengelakkan, to prevent cracking because of the continuity between the slab dengan the beam at the end of the connection, at the end of the landing. So basically, we are looking at this sort of kita punya layout ataupun schematic. We have a beam. Okay, we have a beam at the that can be, we have a staircase that can be represented as a continuous beam, and this continuous beam represents the end span of a continuous punya beam. So the staircase can be considered sebagai continuous staircase. And remember, for continuous staircase, the bending moment punya value would be FL over 10. This would be the formula that we will be using to obtain the bending moment, FL over 10. And similarly for the positive bending moment, again, we'll be using FL bagi 10. Okay, FL over 10. The F is the total force. Okay, the total force on the beam. And because we have dua nature ataupun two shapes combined into a single span. One is the inclined section of the staircase. Another one is the horizontal section. Maka loading that would be resulted due to this combination, we would have a loading that would represent bahagian inclined section, and another loading that would represent bahagian ataupun the horizontal section. And we will clearly see there is a difference between the inclined section loading and the horizontal section loading. So we have these two loadings, W1 dengan W2. Okay? W1 and W2. W1 representing the inclined section, where we evaluate the loading based on the average thickness. Okay? What we have done earlier dalam example number 1. And we have the W2, sorry, yang ini bukan W1, W2. W2 section is the loading representing the horizontal, which is the landing part of the staircase. And clearly nanti kita akan tengok there is a difference which is between W1 and W2, because W1 we are using the average thickness, manakala W2 we are using the actual thickness yang sebenar, this H. Okay, the H. Okay. So when we combine these two loadings together, we have W1 and W2 represented in a single span dalam rentang yang sama. And let's say W1 is, the span for W1 is L1 and the span for W2 will be L2. So to obtain the value of F di sini, because we have a combination of W1 dengan W2, maka to obtain F later on nanti would be W1 multiplied by L1 plus W2 multiplied by L2. So this would be the value of F, the combined total forces between these two components, the inclined section dengan horizontal section. Okay, the inclined section katakan W1, the horizontal section is W2. The length of the inclined section is L1, the length of the landing is L2. So from here, to obtain the value of F, we need to combine both values. Therefore, the simplification to obtain the value of F, the total load on the on the beam ataupun on the staircase, the overall loading would be W1 L1 plus W2 L2 to obtain the value of F. Once we have obtained the value F, we know the value of L. L is given here, starting from the center of beam, center of support on the right hand side, sehinggalah kepada center of support on the left hand side. That would represent the total span of the staircase. So overall, this would be the solution, the direction of the solution that we're going to look at. Pertama sekali, we were looking at the supports. Okay, now the support has been the position of the support has been changed with respect to example number 1. The right hand support has now been relocated to the end of the landing. Okay. And the left hand support remains at the same position as in example number 1. And from there, we can define those two supports as being the supports for the staircase. And we have, from there, kita dah come up with the schematic, schematic of the staircase in terms of beam behavior. Okay, the idealized beam of the staircase, okay, the idealized structure of the staircase, and this is represented as a beam. And clearly on the left-hand side, it is continuous on this left-hand side, and therefore it is continuous di sebelah sini. Manakala on the right-hand side, it stops at the support, and therefore it stops here. So the staircase can be represented as an end span of a continuous beam. Rentang hujung rasuk selanjang. It is still considered sebagai continuous beam. Cuma we will have negative moment from one end ataupun at the left hand support sahaja, with zero, theoretically zero bending moment on the right hand support, and this represents the shape of the bending moment that will be evaluated for this example number 2. Okay, and for the loading that will be acting on the staircase ataupun on the beam, overall we will have two different loadings because we have the inclined section and the horizontal section within the same span. Therefore, we need to differentiate between the loading for the inclined section and loading for the horizontal section. Clearly, there will be a difference. For the inclined section, similar to example number 1, we will be using apa yang dinamakan sebagai the average thickness. Okay, the average thickness will be used as our reference to obtain W1. Whereas W2 we will obtain from the normal thickness of a horizontal member, of a horizontal landing ataupun slab. Okay, and from there kita akan dapat the value of F, which is evaluated menggunakan W1 L1 plus W2 L2. And from there kita dapatlah evaluate the bending moment and provide the top reinforcement at the left hand support. Whereas for the bottom support, we will be using the same bending moment FL over 10 to represent the bending moment at mid-span, and from there kita provide the bottom reinforcement between support on the left-hand side and support on the right-hand side, provide bottom reinforcement. Not forgetting, there is also a top reinforcement di sini. Now this top reinforcement at the end, connection between the slab dengan the beam, is actually to prevent cracking, because there might be some torsional, because it is connected directly between the beam dengan slab. Therefore, we still need to provide some top reinforcement di sini, even though theoretically it is zero bending moment. So this beam reinforcement provided is sebenarnya to prevent anti-cracking, okay, to prevent any cracks at the junction between the beam dengan landing ataupun the slab. Okay, so this would represent the overall solution for the staircase. Another thing is to bear in mind, once we have relocated the support di sini, compared kepada example 1, now the support has been relocated at the end of the landing. We have our span di sini, center support kepada center support, and clearly the span on our example number 2 is much bigger as compared kepada example number 1. And the bigger the span, kesan dia kepada thickness of the staircase. Remember, we had a discussion earlier on how to estimate the thickness of a staircase. Dan to estimate the thickness of a staircase is by using what is termed sebagai our deflection criteria, L over D approximately 30. So by using this L over D approximately 30, then we can come up with an approximate thickness that can be used for the staircase. For example, kita punya total span dia berapa? 27 plus 1.6. 2.7 plus 1.6, 3, 4, 4.3 meters. Okay, so we have an L which is 4,300, 4,300. Okay, we have on the right hand side ni 30. Therefore, we can calculate what is D. Anyone? Aznita? Ataupun Azam? Anyone with a calculator?
100.
Berapa?
143.
143. 143 mm. Okay. So 143 plus our cover approximately around 25 mm. Maka kita dapatlah 168. Around 168 for the value of H. Maka I could specify that the H value di sini, this H value to be used is mungkin dalam 175. My H to be 175. 175. Remember, thickness ataupun dimension of reinforced concrete dalam gandaan 25, in multiples of 25. So kalau 143 plus 25, I have about 168. Maka from there I choose 175 as my thickness. In this example, dia guna berapa H dia? In this example,
160.
160, right? Okay. So in this example, it is using 160. In our estimations, using this ratio as our reference, the thickness is about 175. Okay, and saya savekan yang ini. And if we have a look at the this example, kalau we jump to the deflection criteria, okay, deflection, where L over D, the actual L over D is around 34 allowable, and the actual is about 33.1. So there is a very small difference between the actual dengan the allowable. This is based on 160 mm overall thickness, where the minus ini lebih kurang 30. If I'm using 175, kalau my H is 175, okay, if I'm using my H to be about 175, my D would approximately be lebih kurang lah, lebih kurang tolak 30, 145 minus 30, okay, minus 30. So kalau my D is 145, then what would be this ratio? L over D dapat berapa? 4300 divided by 145. Anyone?
29.7.
29.7. Lebih kurang 30. Approximately 30. Now we can see the difference between 30 dengan 34. It is a bigger difference. It is a safer difference. Lebih selamat sikit lah. So that is why I've mentioned earlier that if we were to use 175, we would have a better control in deflection. Dapat control lah, a better control lah. Bermakna the L over D, actual L over D clearly is much lower than the allowable L over D. Katakan kita maintain allowable 34. Okay, so from here we can see that choosing H175 gives a better control against deflection of the staircase. Even though using 160 is still a safe solution. Kalau dari segi perbandingan 33 dengan 34 is still okay on paper. Okay, on paper it's still okay. Cuma if we were to use 175, it gives a better control in deflection. We have a smaller L over D, actual L over D, as compared to the allowable L over D. Right? So this is comment saya lah, that we can choose to use 175 sebagai thickness of this example, instead of 160 boleh guna 175 sebenarnya. We can use 175, and clearly by using 175 will give a better control terhadap deflection, right? So all of that yang kita bincang tadi, just by looking at the schematic of the staircase. We haven't gone into the actual calculation lagi, but secara rangka, okay, we have come up with all those solution. Berapa bending moment diagram, we have W1, we have W2, how to evaluate F, dan seterusnya. And if we have a look at the solution ni, okay, this is the process similar to what we have done earlier. Based on 160 mm thickness, maka we have an average thickness of approximately 276, 276. The same calculation is applied, okay, R squared plus G squared, square root kan semua sekali, divided by G times H, dapatlah nilai Y, about 191. Once we have this Y value, then the average thickness is Y plus R. Y plus R represents yang inilah, this total value. Y plus R plus Y ni divided by 2. This is the average thickness. And from this average thickness, maka dapatlah our GK. Remember, this is GK due to the self-weight component. Add to this kepada the value of finishes, kemasan, maka the total GK is now 5.2 kilonewton per square meter. The QK value is given as 3.0 kilonewton per square meter. And from here, we have a design load of approximately 11.5 kilonewton per meter squared. Again, kita multiply by 1 meter, so that all our calculation is based on a 1 meter width of the staircase. Okay? So it doesn't matter. Lebar mana tangga pun tak apa. If we don't know the actual width pun tak apa. If it's not given pun, we can still proceed dengan solution dia. Yeah. And finally, kita dapatlah the loading, okay, which is this is the value for the this is the value for the landing sebenarnya, menggunakan 160 because we have a landing which is 160 mm thick. This is my landing, okay, lebih kurang macam tu. And then I have my beam dekat hujung sini. And I have my beam di sini. So this thickness, okay, tebal yang ini for the landing is also maintained at 160 mm. So the thickness for the staircase dengan landing sama, 160. So from 160, maka dapatlah self weight dia 4 kilonewton per meter square. This is the loading for bahagian landing sahaja. We proceed kepada bahagian staircase, okay, for the inclined section. This is the inclined section where we are using the average thickness. Kalau tadi the actual thickness, this is for landing 160. Okay, for the flight ataupun for the staircase, the inclined section, we now use the average thickness, and we have GK total 8.1, and finally we have 15.5. So clearly there is a difference between 11.5 for the horizontal component, the design load, then for the inclined section is approximately 15.5. So we have a clear difference between these two components. That is why saya lukiskan earlier, okay, that the loading katakan for this component, for the staircase component, okay, loading dia besar sikit, and then a smaller loading for the landing, because this value is approximately 11.5 from our calculation, and for the inclined section is approximately 15.5. These are the two values. Clearly, the inclined section loading dia besar because we are using the average thickness. So the GK component jadi besar, QK sama. Incline or horizontal, the QK remain the same. Tak ada berubah apa-apa. Yeah. Cuma for the GK component, the incline and the horizontal is a bit different. Then from here, this is how we evaluate the value of F. Sebab we know the bending moment is FL over 10. Maka F will be W1 L1 plus W2 L2. This is what we mentioned earlier. I've mentioned earlier tadi. Okay. Alright. So from here kita dapatlah bending moment 25.9, top negative moment at the left support dan juga mid span of approximately 25.9. Okay. And daripada sini maka we can evaluate the reinforcement. So what we have here is the main bar H10 at 150 to resist the bending moment of around 26 kN/meter per meter width of the staircase, about around 26. We need this reinforcement H10 over 150 pada penyokong dan juga pada tengah rentang. And the secondary bar is H10 at 400. Right? So this is the solution untuk the staircase example number 2. Okay, and from this selection, maka what we have di sini is shown di sini. Okay, H10 at 150, the main reinforcement again di sini. Please add into your drawings, into your sketch, into your textbook that there must be the top reinforcement on this side, okay, of the staircase. Alamak. Okay, draw lagi sekali. Okay, we need to add additional reinforcement di sini so as to provide sebagai top reinforcement over support. This is a continuous support, so there is top reinforcement. Lebih kurang macam itulah. Yeah. So we need to have yeah. So this will represent the top reinforcement. We need to add this additional reinforcement. Okay, perhatikan di sini the bottom steel will start from center support sini ataupun from the face of the support at the lower end right hand side sehinggalah bottom steel sehinggalah sampai pada penyokong, it becomes the top steel. That is to resist the bending moment from the negative bending moment. And again di sini clearly this reinforcement, the reinforcement yang hitam ni, dotted line ni, again this is the reinforcement from the adjacent slab that is not being designed in part in this solution. Dalam soalan ni ataupun dalam penyelesaian example ni, sebenarnya the black reinforcement dotted line ni is something that is not designed. We didn't design dalam this example. The black dotted line represents the reinforcement from the adjacent slab that is being anchored ke dalam staircase. Okay, so this is example number 2. We have about 1 minute lagi. Okay. Kita take a break, okay, and kita habiskan sikit on the shear, deflection dengan cracking before kita proceed kepada example number 3. Any question? We will save your questions untuk our second session. We'll take a break about maybe 5 to 10 minutes bagi masa untuk saya to compile the video, and then I will remind to you all to join balik. Okay, so saya save yang ini and I stop my sharing sini. Okay, we'll end di sini and maybe about 5 to 10 minutes kita rejoin balik.